representations. You can think of the compiler as a pipeline where each stage job is to organize the data, representing the user's code in a way that makes the next stage simpler to implement. So basically, you can think of the front end and middle end are as steps to convert that to a simpler language that a CPU can understand. The front end of the pipeline is specific to the source language the program is written in. The back end is concerned with the final architecture where the program will run. In the middle, the code may be stored in some intermediate representation that isn't tightly tied to either source or destination forms, hence intermediate. Instead, the IR acts as an interface between these two languages. So there is a front end and back end, and the intermediate representation are the representation or the interface. So the way to communicate from source or front end to a backend is through intermediate language. There are a few well-established styles of IRs out there. Hit your search engine of choice and look for control flow graph. So this is where the environment after the static analysis, the static or the environment where we resolve and we bind identifiers is also a control flow graph thing, a static single assignment. Continuation passing style. So the continuation passing style is where you return the value immediately of a function. And 3, address code. This lets you support multiple source languages and target platforms with less effort. Say you want to implement Pascal, C, and Fortran compilers, and you want to target x86, ARM, and I don't know, Spark. Normally, that means you're signing up to write 9 full compilers: Pascal to x86, C to ARM, and every other permutation. Instead of doing that, you can write one front end for each source language that produces the IR, then one back end for each target architecture. Now you can mix and match those to get every combination. So instead of creating a back end that will connect your source language to the architecture, you can instead create an IR, an intermediate representation that will then be can be connected or can be compiled to those late architecture. So if you ever wondered how GCC support so many crazy languages and architectures like Modula 3 on Motorola 68K, now you know. Language front ends targets one of a handful IRs, mainly Gimpol and RTL. Target backends like the one for 68K, then take those IRs and produce native code. So the GCC which was written in C are compiling or targeting the compilation to the handful of IRs such as Gimpol and RTL, and that Gimpol and RTL is what allow the Motorola 68K to take those IR and produce the Motorola native code. Now there's another big reason we might want to transform the code into a form that makes the semantics more apparent, which is optimization. Once we understand what the user's program means, we are free to swap it out with a different program that has the same semantics but implements them more efficiently. we can optimize it. So once we understand the source language and then transform it to a syntax, and then represent, we have an immediate representation ready to be executed in the late architecture, then we can represent the program in a more efficient way so that the CPU could execute it more efficiently. A simple example is constant folding. If some expression always evaluates to the exact same value, we can do the evaluation at compile time and replace code for the expression with its result. So it's like with how the database compute or store raw data instead of compute, because it allows you to avoid having a stale database data, while at the same time allowing you to compute it fast because you have the computed value already, because you already done the hard work in compile time, kind of like in compile time. So if the user type in this penny area equals 3.4159 times 0.75 slash 2 times 0.75 slash 2, we could do all of that arithmetic in the compiler and change the code to penny area equals 0.4417860,938. Optimization is a huge part of the programming language business. Many language hackers spend their entire careers here, squeezing every drop of performance they can out of their compilers to get their benchmarks a fraction of a percent faster. It can become a sort of obsession, but many successful languages have surprisingly few compile time optimizations. For example, Lua and CPython generate relatively unoptimized code and focus most of their performance effort on the runtime. So because this optimization has a lot to do, or has more to do with the compile time, where you're trying to convert it into a CPU, a lot of successful languages were able to be successful without this optimization into its late architecture, but instead focus their optimization in runtime or in the user space part. Now, if you can resist poking your foot into that hole, some keywords to get you started are constant propagation, common sub-expression, elimination. So a sub-expression, if there's a common nested sub-expression, you will eliminate, kind of like eliminating that space in that module. Loop invariant, code motion, global value, numbering, strength reduction, scalar replacement of aggregates, dead code elimination, and loop unrolling. Code generation, we have applied all of the optimizations we can think of to the user's program.